Now I'm starting the recording for the second day of Intro to Astro. Okay. So what are we doing today? Okay, so there's a reading due today, which most everybody got, and I'm pretty stoked about that. I didn't get through everybody's questions because I ran out of time because I started a little bit too late. So there's a couple of you that I didn't get to your questions yet, but I'm going to go through the rest of them. So if I go through the questions and you don't see your question up there, don't feel bad. It's because I flaked. I promise I won't do that on the regular. And if you still have your question, if you don't see your question up there when I go over the questions, which I'll do first, you can just holler, like just raise your hand and we'll talk about it. Okay, the first numerical homework is due. Promise I'm. Is there a garbage can in here? That way I'll stop eating. Right. Aha. That way I won't be eating and talking at the same time because that's kind of rude. Okay, first numerical homework is due Friday. It's not super painful. It's just download Anaconda and run through this one notebook, save the notebook, turn it back in. It's just, it's really, the assignment is really mostly orientation. So just making sure that you guys know where the stuff is and how to get Jupyter and make sure that Jupyter works and all that. So it's not super painful. That being said, I'll have office hours 2:30 in my office in 608 Keene. If everybody shows up, my office is not big enough, and I'll move to 621, which is just around the corner. So there'll be a sign at my door. So go to 608 Keene. If the office door is closed, go to the conference room, which is around the corner. It's also on the 6th floor. Hope everyone had a nice and productive hurricane. Is this your first hurricane? No? So there have been many in this part of town in the last couple of years. So if this was your first hurricane, sometimes they're worse than that, and sometimes they miss us completely. So that was a really fortuitous hurricane for us to have. So always don't let that one, when the next one comes in like 2 months, because end of August is super early in hurricane season for us to get an actual hurricane. So when the next one comes, don't be slack. Make sure you prepare just like it was going to kick your ass. So, okay, so today we're going to talk about the Earth and space. And this is my first lecture at 50 minutes with actual content in it. So I have absolutely no idea how long it's going to take me to get through this material. I'm pretty sure I'm going to end a little bit early. If I do, I'm going to pregame Friday's lecture a little bit, but not a ton. So we'll talk about the real stuff. We'll talk about Newtonian mechanics a little bit. So what are we doing? Let's talk about the Earth in space. So the Earth. I'm going to draw pictures. So I'm going to do. Please speak up if this board does not work for you for whatever reason. But I'm going to try to do the work on that. I'm going to see if I can source a dot cam and play with that too, but that's all horse around about later. For now, we'll use this board. So the Earth moves around the sun, and it took us a long time and lots of power struggles between powerful people and who know what's going on for us to actually. This is a very nice diagram of the lens. So the Earth. I gotta turn this thing so I can see where I'm at. Video. Oh, and I haven't posted the first video yet either, because I don't actually say anything other than stuff that you already know and stuff that's in the syllabus. I promise it'll be up kind of right after class most times. Okay, so here is the Earth. No, here's the sun. Let's draw the sun like this. The Earth doesn't have rays. The Earth orbits the sun on an elliptical plane. It's mostly circular. I drew it a little exaggerated here. It's not this off center. It's pretty round. The Earth orbits the sun on an elliptical plane, and the sun and the Earth has an axial tilt of how many degrees thereabouts? 23 degrees. So the Earth has a tilt of 23 degrees. And that has significant impact on the state of the Earth. So what does the Earth look like? How is it doing? And how we see out of the Earth and find things in the sky. So as I've drawn it, okay, so the Earth is like this. Let's try a voter question real quick. Okay, so did everybody bring their voters from last time? Did anybody not? That's all right. If you just have a piece of paper, that'd be fine. I'm going to try to remember to bring a whole stack of extras in the future. So, so we're just going to have a two-channel vote. Which one of these is summer? Is this summer, or is this summer? A or B? What was that? Oh, for us, in the northern hemisphere. And north is this way. Aha. All right, so most everybody said it right. So, okay. Okay, take a second, talk to your neighbor. If you've got a different answer, talk about it.
I figured it out.
No worries?
I was like, oh, you skipped more because the more amazing, but then
Yeah.
wrong. Yeah.
But your logic is right. You just had the picture wrong. So
Yeah. We got it. We're good. Yeah. Okay. You know, I was the one who was wrong.
all right, so I'm pretty sure that everybody's mostly on the same page. So I'm going to interrupt, and let's talk about, as a central group, let's talk about our logic. So what's the big difference between the amount of light that someone, let's put us on this Earth, say right here. What's the big difference between the light that somebody here receives versus the light that somebody here receives? Just somebody yell something out.
The amount of air in between?
A little bit the amount of air in between. Somebody yell something else out.
The amount of light that hits on the actual Earth.
The angle of the light?
Like the angle, yeah.
The angle of the light. So that's the biggest thing. So the amount of atmosphere does have an impact, but really the amount of photons that hit the light, it's a cosine of theta suppression as you move away from the line of sight. So if I have a surface like this and I have photons coming at it, I have all of those photons concentrated on this spot, right? If I tilt it at an angle, then those photons are spread out over this much space, which is more. So any unit of area gets fewer photons per unit area. So here, when the sun is at a strong angle to us, the sun at noon is at 23-degree angle to us, or something like that. There's a large angle between this flat surface of the Earth and the direction the sun is coming. Later in the year, the sun is much lower in the sky, so the angle is much larger, so we get a lower fraction of the photons. And that is the primary reason for seasons. This also impacts other things we know. So one of the reasons that I'm talking about seasons, even though this is an astrophysics class and I'm not going to talk about terrestrial things very much, is because we use the seasons to find our way around in space, which took me a minute when I first learned this. What does it keep doing? I see this thing out of the corner of my eye jumping around and doing stuff. Why does it keep doing it?
I think the HDMI connection
Might be loose?
yeah.
Okay. I'm not going to worry too much about that yet. So we use the seasons as points on the sky, which is a little strange because the season is like a state. It's like whether it's hot out or not a location in the sky. But we can understand how to use the seasons as geometry this way. So if here's the sun and here's the Earth. So when the Earth, here's something that I need to talk about. How does the angle that this makes relative to the plane change from day to day? The position of the pointing of the Earth. As the Earth moves around, how does its direction that it's pointing change? Does it change a lot? Does it change a little? The way I drew it, assume the way I drew it is right. Does it change it? Or does it change at all? No, it stays pointing the same direction. Why?
Because of gyroscopes.
Because of gyroscopes. What's the conservation law? What's the thing that's conserved that keeps things that are spinning? Angular momentum. So the angular momentum is conserved. Okay, now there's precession we'll talk about in a second. Still conserved. But the bulk angular momentum is conserved. So the Earth is spinning. It's going to keep spinning that way unless you do something substantial to it. So the Earth always basically points, and I'll tell you how it changes in a second. The Earth always basically points in the same direction. So now there's a point when the rotation axis is pointing straight at the sun. And there's a point where the rotation axis is orthogonal to the sun. So sorry. So when we look at this one, which one of these is going to be summer? This one, this one, this one, or this one? Somebody just yell. Can you tell? So this one or this one, now this is a little degenerate because you can't see which direction the tilt is. It's going to be one of these two because this is where the pole of the Earth is pointing directly at the sun, and one part of the sun, one part of the Earth is going to be getting the most amount of light, and the other one is going to be getting the least amount of light. So this is called what? What do we call these 2 points in the year? The solstice. So these are the solstices. And the other two are the equinoxes. Now this one you can remember what it means because equi is equal and nox is night, right? So these are the equal day, night times. So, and you can tell by the geometry, if you're at a point here and you rotate around, you're going to see the same amount of day and night. Whereas if you're up here, as we rotate around, you're going to see a lot less daytime or nighttime, depending on the hemisphere you're at. The other thing that impacts the seasons is how long the day is, because the angle also changes where the shadow of the sun lies. So how do we use this to define our coordinate system? Because that's really what I'm going with this. I don't really care about it being hot outside. Well, I do. It's kind of a drag. But. So how do we define this as a point in space? So we're going to define our coordinate system for things that aren't in this system using this. Let's talk for a little second about coordinate systems that are obvious real quick. So let me pull up my notes. Where's my doer? There you are. I forgot the important geometry. I'll come back to the important geometry. We'll talk about that in a second. Yeah, okay, so we have several things that we need to define. So the plane that we orbit in is called the ecliptic. And that is the plane that all of the planets basically orbit in. Now, they're not all perfectly in exactly the same plane because there's a little bit of wobble when things perform. But for the most part, all the planets are orbiting in the same plane called the ecliptic. And we can see the ecliptic by looking at where the planets are or where the sun is. The sun and all the planets and all the comets and all the moons all live in the ecliptic. So we can so we need to define some coordinates. So let's talk about coordinates for a second. So I want to know where a star is, say Betelgeuse. Actually, let's look at the star Rigel, because I can spell that. I have a hard time spelling Betelgeuse correctly. I want to know where the star Rigel is. So the easiest thing to do is the alt-as coordinate system. And this is measured from the North Celestial Pole. I haven't defined that yet. What is the North Celestial Pole? It's the North Pole, but on the sky. So the Earth has an axis that it rotates about, and the points where the axis is they're imaginary, but we call these poles. We call these poles because that's what we call that point in the coordinate system, so it's a geometry word. So this is the pole, and there are several poles because there are several things you could define several ways you could define the axis. So there's the rotational pole, and that's the point on the Earth where everything is rotating around, and that's the North Pole. There's the magnetic pole, which is actually more important for a lot of reasons, because that's how we do all of our navigation, which it coincidentally points along the North Pole. It happens to be close. There's reasons for it, but it's complex. It doesn't have to be. And then we have the North Pole on the sky. So now, the North Pole on the Earth is the point where if you hold still there, everything spins around you. The North Pole in the sky is a point where you take a picture of the sky and everything spins around the North Celestial Pole. Does that make sense? So it's the center of the spinning of the Earth. So we define everything relative to the North Celestial Pole. We have this really nice star called the North Star that happens to sit basically right there, coincidentally, but it's very nice. So we can use this star to do a lot of our navigating. So the Alt-Az system is pretty straightforward. You have the equator. So here's the sun. Here's the equator. Hopefully the sun is down when you're taking your telescope measurements. It's easier to see things when the sun is down. But if I think about the equator as a circle that goes all the way around me, so north will be up here, south will be down here, east will be down here, west will be over here. It's nice that I made the sun setting in the west. I didn't plan that. That was so if I think about this as a circle, then this is north. So this line wraps around. Right? I'm just flattening it out so that I can draw it. So then the sky looks like this. The North Star is up here. We measure our altitude and azimuth. The azimuth is the distance from the North Star, and the altitude is the distance from the equator. And the azimuth is the distance from the North Pole. And these are all measured in degrees, because we like degrees. But what's the problem with this coordinate system?
It's location-based.
It depends on your position. It also depends on time. So where I am in the Earth, if I'm here, the horizon is here. But if I'm up here, the horizon's up here, and that's going to move my whole zero from my coordinate system. Where I am determines where the horizon is. So that's a drag number one. Drag number two is as I sit here and I watch Rigel, it moves. And that's also a drag. So the altitude and azimuth are time dependent and location dependent quantities. But if I have a simple telescope, if I have a telescope that just goes up and down, it's called a Dobsonian mount. That's really easy to find a star. I just point to where it is, and then I point up to see it, and then I look through the eyepiece and I can see it. And that's using the Alt-Az method to find things using a simple telescope. So it's easy to use, but it's hard to use precisely. Now, intrinsically, it's just as precise as RAN DEC, provided you have a good clock, but you need a good clock. So it's a little hard to use precisely. What we use for precision and for consistency is called the right ascension and declination. So we have a similar scenario, but I'm going to erase this picture because it's not very useful. We're talking about this picture now, where we're talking about the Earth in space. So this is the Earth sits in a galaxy, and there's a big spiral arm here, and there's a local bubble, and the Earth-Sun system is also going to basically point the same direction all the time because, again, angular momentum is conserved. So if we look at the plane of the ecliptic is always pointing in the same spot in the sky. But, I mean, okay, we're moving through the galaxy. The galaxy is not a static object. It's evolving, and it's going to crash into another galaxy. So everything's moving a little bit, but for the most part, this is a very stable system. So if I want to know where I am in space, I've got all these stars out in outer space. Some are close to us and some are far away from us. Well, we're going to assume that we're only going to think about the ones that are really far away from us because they're not going to move very much with time. The ones that are close to us will move with time in ways that we can predict. But we need to define the coordinate system. So what we do is we say, okay, the vernal equinox, we're going to call this point upsilon. Now, we're going to define this as a point on the sky when the vernal equinox happens. What does that mean? So this is moving, right? It slides around like this. There's one point in time where the axis of rotation is most perpendicular to the line connecting the sun and the earth. Does that make sense? So this line is most perpendicular to this line. Now I have absolutely no way of measuring that in real life. But I can look at the stars and say where they are. So I can say, what is overhead at midnight UTC? What's UTC? Does everybody know what UTC is? This is the universal coordinated time. So this is time for the planet that starts at in Greenwich, England. So midnight at Greenwich, England defines universal time. And this is just defines the time zone. So we're at UTC minus 5. That's our time zone. So at midnight, universal time, so that's midnight in Greenwich, England. Whatever is overhead at the vernal equinox, which is this point exactly, defines where the point is in space. So we'll go out this way, we'll draw this line forever, and that defines the vernal equinox. Right? So it went from the day when the nights start getting longer. No, wait. Yeah, vernal, right? Vernal's spring. So after the vernal equinox, the nights start getting longer, the days start getting shorter. That's what it means for me and me as a person who raises children and needs to put children to bed at a certain time every day. So that's what it means for me. But from an astronomer's point of view, which is also me, it's a coordinate in space where we measure everything from. So when the Earth is here, it defines here. Now we don't really need to think about this too much. It's just how we defined it. So we'll just do all of the rest of our geometry from here. Now I'm not going to get into the details of coordinate converting between the two systems because it's kind of a headache, and there's tools that just make that easier for you. But I'll tell you about the two systems. So we define two coordinates. Again, let me draw like this. So now I've got my Earth, and I've got my axis of rotation, and then I have the ecliptic. Let's see if we can just do this in some. So this is the ecliptic plane, and this over here is the vernal equinox. It's a point in space. The Earth spins around, Earth moves around, vernal equinox stays at the same spot in space. So we measure our RAN deck as you go from the ecliptic and measure up from the ecliptic, and that's the declination. So we define the declination as the distance in degrees from the ecliptic plane. Now this is different from the horizon. So Alt-Az goes up from the horizon, but the horizon moves and depends on where you are and who you are. But the ecliptic is the same for everybody. Now it moves on the sky, but that's okay. It moves in a prescribed way that we can take out. So declination is the distance from the ecliptic, and right ascension is the distance in hours, minutes, and seconds from the vernal equinox. So that's here. So if I've got a star that's, say, here, we would measure that. I would go up like this, and I would go around like this, and that would give me a star that's there. So, two things. One, RI and DEC are the coordinates for objects. So that's how we define the coordinates in outer space. They're measured in two different units, which is a little annoying, but is actually awesome. Because why? Because declination is measured in degrees because we're measuring an angle and we like degrees. Right ascension is measured in hours, minutes, and seconds. So let's talk about that for a second. What do I mean by that? So when, oh, actually I gotta talk about degrees and arc seconds. So I have 1 degree. How many degrees are in a circle? 360. So 1 degree is 1/360th of a circle. 1 arc minute is 1/60th of a degree. And and it gets just 1 tick. The smaller one gets 2 ticks. I don't know why. If you're looking at feet and inches, people will often write 4 feet to mean feet with a little tick up there, and 2 ticks means inches. This is similar. 1 tick means degree, arc minute, and 2 ticks means arc second. So an arc second is 1 arc minute over 60. So there are 3,600 arc seconds in an arc minute. Does that make sense? So we talk about arc seconds and arc minutes a lot because they're little fractions of a degree. Now a degree isn't very big. An arc second is actually a very small quantity. It's a very small piece of an angle. And what we really need to do is to talk about milliarc seconds and microarc seconds if we really want to get the parallax right, which we'll talk about in a minute. So that's declination. Right ascension is measured in hours, minutes, and seconds. So the reason for that is because that's an easier way to find where you are on the sky in the direction that the Earth is spinning, because how long does it take for the Earth to go around the axis? 24 hours. So we can break the sky up into 24 hours. Make sense? And then we can break each one of those hours up into minutes and seconds. So we can also break the sky into 1 hour, 1 minute, and 1 second. So that's handy. How do I know, or why is this handy? Because if I have something and I know it's right ascension, and I know what's overhead, then the difference when that object will be at overhead is the difference in right ascensions. That's the time that it will take for that object to be overhead. So if I have an object that's overhead and I know it's right ascension, and I have a right ascension that's an hour away, I just need to wait an hour, and then it will be overhead. Does that make sense? So the right ascension is in time because it's an important quantity because the Earth moves. So when you're converting between alt and as and RA and DEC, that becomes very important. Actually getting the RA and DEC and the alt and as is a headache, and I'm not going to go through it right now. Does that make sense? Does anybody have any questions? Yeah.
So for the Earth, is 1 hour equals 1 degree?
No.
Cool.
How many degrees are there? Well, I got a circle. How many degrees are in a circle?
360.
360. And how many hours are in a circle? 24. 24.
24. Oh, okay.
So how many degrees are in an hour? 360 divided by 24, which is 15.
Okay.
Right? Now, how many arc minutes, how many arc seconds are in 1 second? This is a very easy question. It's also 15. I get them the same way. They're both a minute. An arc minute is a 60th of a degree, and an arc second is a 60th of an arc minute. Same thing with hours, minutes, and seconds. This minute is a 60th of an hour, and a second is a 60th of a minute. So it's 15 all the way across. So you just need 15. So 1 hour is 15 degrees. How big is 15 degrees?
Half 30 degrees.
Half the 30 degrees. That is not a wrong answer. Let's see. Do the thing. Okay, did I talk about all those things? I think so. Yeah, okay, so, what's that?
1 minute is 15 arc minutes, right?
A minute is 15 arc minutes.
And then
Yes.
1 second is 15 arc seconds.
That's correct. Exactly. So this is kind of awesome. Everybody's hand is a different size, and everybody's arm is a different size, but their ratio is about the same. So if you hold your arm out and stick up your thumb, regardless of how long your arm is, your thumb is going to be the same size and proportion, and that's about 2 degrees. So your thumb is about 2 degrees. Your fist is about 10 degrees. And if you make the Ronnie James Dio horns, the tips of the horns are about 15 degrees. So if you want to know where the sun is and when the sun is going to be somewhere else, that the sun will move from here to here in an hour. Because that's 15 degrees, and there's 15 degrees in an hour. Right? So if you're sitting on the back of your surfboard waiting for the sun to go down, and you want to know how long it's going to be before it gets dark, you can just do that a couple of times. Then you know how much longer you have before it's too dark to surf. For instance, the reason that's comes to mind is that's the one time in my life where I've really needed to be able to judge time accurately because I don't have a watch that's waterproof. So I'd be out in the ocean and want to know what time it is, so I could kind of basically guess using that. Okay. So you can use that. That's very handy. So a fist is 10 degrees. Or how many minutes? About 3/4 of an hour. Okay. Everybody good so far? I'm actually going to stop here for a second, and I'm going to go over the questions. So I wanted to start and just like talk about the basic stuff before I went over the questions, because some of the things I knew I was just going to say. So let's go. A couple of these are missing. If I get to the bottom and you have a burning question, even if it's a basic question like what's a light year, I'm happy to talk about it. Let's see. How am I doing? 1:54. Oh, I got 15 minutes left. Okay, cool. So, what is an arc second? An arc second is 1/360th of a degree, 3600th of a degree. What is this great circle business they keep talking about? More than one of you asked this. One of you asked the question and then later on stuck sticky notes next to the thing with the question answered, which I really appreciate. Because that reminds me, when I was in grad school, I would go into my advisor's office and explain a question to him. And by the time I got through actually explaining everything that he needed to know where I was at, because your advisor never knows where you are, right? And then the problem, I usually had solved it. So it's a fun. So anyway, keep asking questions though. So what is a great circle? I do need to talk about this. This is an important geometrical structure. So everybody knows what a line is, right? Everybody gets a little hesitant because they think they know, but you know I'm going to ask you, so I'm going to make it funny, right? So a line is the shortest distance between 2 points. Full stop. That's what a line is. So on a circle, if I'm constrained to be on the surface of a sphere, and I take these 2 points, how do I find the line that joins them? Now this is really fun if you've ever flown to Europe, especially in North Europe. So when you fly to Europe, you go over Greenland, which doesn't make any sense if you look at the wrong projection. But if you look at a globe, it makes perfect sense because Greenland lies in the Great Circle. To find the Great Circle, you take your 2 points and you take the center of the Earth and you draw a plane that passes through all 3 of those things. Okay? I was going to get a globe, but I forgot. So if you have a globe, I have 2 points on the globe, you take the center and you take a plane and you draw the plane through those points. And that defines the Great Circle. Because the circle is actually the size of the whole planet. It's the biggest circle that you can draw on the sphere, right? because it takes up, it's always going to be the circumference of the whole circle is always the circumference of the planet. What you want is just the part on those lines that connects your 2 points. So we talk about great circles, and there are a couple of great circles that that we often talk about. So there are many great circles, but the important great circles that we talk about a lot go through the North Pole. We like these because they're useful for navigation, and we call these meridians. But a meridian is just a great circle that runs through the North Pole. Does that make sense? Yeah.
So it's like this place you go when you, it's like the circle you go when you do this place of the globe?
Yeah.
Okay.
Yeah, you pick your point and the other point, and you cut the globe in half there.
Okay.
And that's the line you get. Every great circle bisects the planet. By definition, it goes through the center. What is the purpose of the parsec as a unit? So it's at the 0 level, it's a space unit, so it's just a unit of distance. We use it as the basic unit in astronomy because it's what comes out of the geometry of the easiest way to find distances. So distances is the biggest problem in astrophysics, full stop. The hardest thing to do is to know how far away something is. Okay, what's going on inside may be a lot harder. It just exploded in a fraction of a second, so you don't know what's going on. But if you don't know how far away it is, you're totally hosed. So distance is the kind of linchpin of basically every astrophysics measurement. And the easiest thing to get out of it is a parallax arc second. And I'll talk about parallax in a second, but basically the parsec is the thing that comes out of our basic distance measurement. So our basic distance measurement is we go around the Earth, or we go around the sun. Here's the sun, here's the Earth again. And at 1 second of arc, that defines 1 parsec. I'll explain this again in a second. But because of this geometry, the parsec is very useful. The other reason that the parsec shows up as a parsec is from basic geometry and an AU. So a parsec is 205,000 AU, and that is arc seconds measured in radians. I'll explain that again in a second. Do I have to memorize the equations? It's a super useful question. That kind of depends on you. However, I am generally of a mindset of you want to memorize as few things as possible. The nature of this class is that you're probably going to have to memorize a bunch of stuff because I don't want you deriving everything. But in other classes I teach, I want you to memorize 1 equation and then derive everything from that. So try to memorize as few things as possible. That being said, there might be a lot. So we'll talk about this when we get to the final. We can go through what you have to know and what you don't a little bit better. What's the North Celestial Pole? It's the North Pole, but on the sky, and it's only defined by the rotation of the planet. Whereas the magnetic pole, if you bust out your compass, that's going to point to the magnetic pole, and that has to do with the geodynamo underneath our feet. How do you convert coordinates? I'm not going to tell you that. Because it's complicated and I don't need it for now. If you really want to know that, take the Astro lab, because I think they go through those details in the Astro lab. Let's see. Can parallax be used to determine the distance to anything or just stars? Everything, but it's got to be close enough. And that's the important part. Let's see. Which coordinate system is used most widely in astronomy? RA and DEC. That's the thing that every star gets. Every star has an RA and DEC. And then we can talk about galactic coordinates. Where is it in the galaxy? We can talk about the equatorial coordinates. Let's see. How would you use calculus to determine the distance to the star using the equatorial coordinate system? I wouldn't. I would. Well, okay, so the idea is you have to measure the star at the same time of day, but it's tricky because you have to take out the motion of the Earth, because in principle, when you're using parallax to measure where a star is, you measure the star at one point in the year, and then you measure the star at a different point in the year, and the star is going to be in a different place on the sky. So unless you correct for the motion of the Earth, then you're not going to be able to use parallax. But if you correct for the motion of the Earth, then you can use parallax just fine. So it works the same as long as you account for the thing that changes. Okay, how close? I'll get to that in a second. Let's see. I'm gonna put the questions that I'm not answering yet down here. Yeah. Does the small angle approximation contribute to error and parallaxes? No, because when you do it for real, you do it for real. Like if you're actually using the Gaia measurements and you actually want an accurate thing, then what they do is they measure the star's position over the course of a year, and they get an ellipse, and they fit the ellipse to the motion of the Earth, and it's all super complicated. So no, because we don't actually, like, you don't actually do it the way I'm going to tell you. You only do it the way I'm going to tell you if you're trying to do it at home. If we're doing it professionally, like for judging where things are in the sky, then they don't use the small angle approximation. They use other approximations which are way uglier. Okay, so which one is more accurate, RA and DEC or Alta as? RA and DEC doesn't move with time, so you don't have to have a good clock. That being said, to find out where you are, you also need a good clock. You need to know what time it is. So they're about the same ultimately. The motion of the ecliptic. Let's see. Do I have? I forgot to put this figure. Let me see if I got it in here. I have a copy of the book. I have a digital copy of the book, and it's great, except like every 10th page is just corrupted and broken. Yeah, it's a kind of a drag. Like, look at all of these awesome things that I'm missing. Anyway, this is what I get for stealing. Aha! I get the top half. So guys, one of you had asked, please explain this diagram. So I'm going to explain this diagram, but I got to draw the diagram first so that I can explain it. So this is a map of the ecliptic versus time. And it goes like this. So this is in day of the year, and here is 0, and here is plus 23 degrees, here is minus 23 degrees. So this is describing where the sun is in the sky. This is the winter solstice, and this is the summer solstice. No, the sun's highest here. It's when it's highest, right? Is when the summer solstice happens. And then the equinoxes are where the ecliptic crosses 0. So why is that? So as the Earth moves around the sun, where it is relative to this plane changes. So you can see that the sun, so this is the equator, let's say. The sun is below the equator here, right, and above the equator over here. The sky, and if I'm taking the vernal equinox as a fixed position, the sun is going to be in a different spot relative to the vernal equinox as I go around the year. Right? So it's going to be below the horizon at the winter solstice, but above the horizon at the summer solstice. And it's a sine just because we're going around in a circle, and whenever you turn a circle into a line, you get a sine wave. Does that make sense? Okay. How am I? I got 10 minutes left. Oh, fascinating. I didn't get through everything I wanted to. Where's my slides? Oh, there. Okay, some of you asked about archaeoastronomy, and I know nothing about it, so I cannot tell you anything. I'm pretty sure that the space aliens did not build the pyramids. I'm pretty sure I have opinions about aliens, so. Let's see. Are high-class lasers used to pinpoint spots on an object when calculating distances, and how can we use that in astrophysics? So lasers are used in LiDAR in terrestrial applications to measure distances, and they use all this same geometry. It's all using, all using the same geometry of parallax that we were talking about here, except it does it with a billion lasers. That's impossible to do with astrophysics except for one specific case. So the one time where we can use lasers to help us out are with laser guide stars. So here we bounce a very bright laser off the upper atmosphere, and we get a spot that is holding still relative to the motion of the lower parts of the atmosphere. It's a very cool process. And then, because you know that that spot's not moving, you can just say, okay, that spot's not moving. Just wiggle the camera so that that spot stays still. It's very cool. I may have interpreted that question incorrectly. Feel free to ask it again. Let's see, what coordinates do space-based telescopes use? They all use Ariane-DEC, because Ariane-DEC doesn't care about the planet. Ariane-DEC cares about outer space. It's about things that are far away from us. It's about the vernal equinox, and it's about the ecliptic plane. And those are the same regardless of how close to the planet you are. So even if at L2, which is far away, we still use Ariane-DEC. How do we account for the star's natural movement due to gravity of other objects? So every star is moving. And this is an important thing. One of you had asked to discuss transverse velocity. So let's talk about that too. I think that's one of the questions up there. So we live in a galaxy. Here's my galaxy. These are spiral arms. Here's the bulge. And we're here, about 8 kiloparsecs from the center. And everything is moving. There's nothing that's not moving in the universe. Everything is moving. The galaxy is moving. These bits are moving faster than these bits, and these bits are moving the same speed as these bits, but they're all moving, and they're all sloshing in and out, so they're moving around. They're not just moving around in a circle. Things are sloshing in and out. So the existence of the galaxy makes everything move a bunch. Now it's important that we know if they're moving relative to us. All of the stars are always moving. Now if I look up at the sky, and I look at a star in 3 dimensions, so here's 3 dimensions, here's me, here's this star. It's got some 3-dimensional angle for its velocity. So it's got some velocity. It's moving some, for all intents and purposes, random direction. It's not a random direction because I understand how the differential rotation of the galaxy is working. I understand how this works. So these stars are moving faster than these stars in ways that are very predictable, for the most part. Then on top of that predictability, there's a random component that is the 3-dimensional motions. There's two motions that are important. There's the radial motion and the transverse motion. The radial velocity is along the line of sight. That's either going away from me. If I draw a vector like that, that's going away from me. So the radial velocity is either going away from me or coming towards me. So it's either positive or negative. And the transverse velocity are the other 2 components of the velocity. And that's going to be somewhere in this direction. Which one of these do you think is harder to measure, the radial velocity or the transverse velocity? And why? Well, I don't need to actually open a discussion because we're low on time. The radial velocity is way, way, way easier to measure than the transverse velocity. A little counterintuitive.
Is it because of redshift?
It's because of redshift. Because everything has a velocity relative to us, and all those velocities are large, and if we have a spectra, we can measure the velocity very easily. So if I've got something that's emitting hydrogen, I know exactly how fast it's going away from me. Does that make sense? So the radial velocity is relatively easy to measure. To get the transverse velocity, you have to just wait, and it has to be close enough. because the transverse velocity for an object here is going to be whatever it is, but the angular velocity is going to be large than another object that's the same, moving at the same physical velocity, but twice as far away. Its angular velocity is going to be a lot smaller. The transverse velocity gives you the proper motion. Which is the left to right motion of the star in degrees per time. Is the ecliptic the same as an elliptical? Well, they're the same, but the ecliptic is just the plane that cuts through it. And then the elliptical path follows along inside that plane. Radial and transverse velocity. The benefits of AU of parsecs over light years. So parsec is more natural because it comes out of the geometry. And I'm out of time. I'm out of time, so I'm just going to stop talking and pick it up. We had a 2:10, right? All right.
Does it start at 1:20?
Yeah.
Then yeah.
Okay, sweet.
Yeah.
Okay, so I'm going to stop there, and we'll pick it up on Friday. Homework is still due on Friday. The reading is still due on Friday. I'm going to race through the parallax stuff because it's actually pretty straightforward. Because the next stuff is hard, so I want to make sure that I get to that. So have a good rest of the day, and I will see you